On 18th June 2023, Titan, a submersible operated by the company OceanGate, imploded during an expedition to view the wreck of the Titanic in the North Atlantic Ocean off the coast of Newfoundland, Canada. Formerly known as Cyclops 2, Titan was a 5-person submersible operated by OceanGate. The 6.7-metre-long 10-ton pressure vessel was constructed from carbon fibre and titanium. The pressure vessel consisted of 2 titanium hemispheres with matching titanium interface rings bonded to the 2.4-metre-long carbon fibre wound cylinder. One of the titanium hemispherical end caps could be detached to provide the hatch and was fitted with a 380mm diameter acrylic window. While myriad issues likely contributed to the vessel's demise, Titan's carbon fibre hull has drawn particularly scrutiny, especially because it was one of the first submersibles to use such a material. Carbon fibre reinforced plastic, CFRP, is a material consisting of several constituents: a base or carrier substance, also called matrix, and a second reinforcing component, the carbon fibre, which is embedded in the matrix. CFRP is a composite material renowned for its high strength-to-weight ratio, making it a preferred choice in various high-performance applications such as aerospace, automotive, and sporting goods. The unique properties of CFRP arise from the combination of carbon fibres and a polymer matrix. The performance characteristics of CFRP are significantly influenced by the orientation of the carbon fibres within the polymer matrix. Carbon fibres are incredibly strong along their length, but relatively weak in other directions. Thus, the orientation of these fibres in the matrix is crucial to achieving the desired mechanical properties. Common fibre orientations include unidirectional. Fibres are aligned in a single direction. This orientation provides exceptional strength and stiffness along the direction of the fibres, making it ideal for applications where loads are primarily in one direction. Bidirectional cross-ply. Fibres are woven into a fabric, providing strength in 2 perpendicular directions. This orientation offers a balance of strength and flexibility, useful for components that experience multidirectional loads. A commonly shared misconception about the material strength of CFRP is shown here in the following video. This video shows a 3-point bending test of a CFRP and a titanium specimen. The titanium specimen carries about 3 times the load until failure compared to CFRP, and therefore people concluded that titanium is much better than CFRP. But this video doesn't show the whole truth from an engineering perspective. From the looks of it, both test specimens are about the same dimensions. Titanium carries 3 times the load until failure compared to CFRP, but titanium is also about 3 times heavier. So in terms of load-to-weight ratio, both materials are about the same in this 3-point bending test scenario. In a pure tension test scenario, CFRP can handle about twice the load of titanium. In a pure compression test scenario, it is about as good as titanium. The main difference is the failure mode of the material. CFRP is brittle, which means it breaks instantly when its material strength is exceeded. Titanium is ductile and carries still some load after exceeding its yield strength and doesn't break immediately. The brittle failure mode is the main disadvantage of CFRP because it doesn't allow any errors in design calculations. The CFRP cylinder of the Titan was manufactured 2 times. The first version was built in 2017 by Spencer Composites. The carbon fibre hull of the Titan features alternating layers of UD prepreg in the axial direction and wet wound carbon fibre filaments in the hoop direction. The second version was built using automated fibre placement by Electro Impact in 2020. The cross-section of the second CFRP cylinder has 667 layers of CFRP and is 127 millimeters thick. The manufacturing process of the CFRP cylinder works like this. A mandrel, which serves as the core around which the carbon fibers are wound, is prepared. The mandrel can be made from various materials, including metal, plastic, or even dissolvable materials if the mandrel is to be removed after curing. The filament winding machine is set up, which consists of a rotating mandrel and a fiber delivery system. Carbon fibers, typically pre-impregnated with resin, known as prepreg, or dry fibers that are wetted with resin during the winding process, are fed from spools through tensioners to the winding head. The mandrel rotates while the winding head moves along its length, laying down the fibers in specific patterns. Multiple layers of carbon fiber are applied to build up the desired wall thickness. After winding, the composite material is cured to harden the resin and lock the fibers in place. The curing process involves heating the mandrel and wound fibers in an oven or autoclave, following a specific temperature and pressure cycle. Once curing is complete and the composite has solidified, the mandrel is removed. The design of the Titan can either be done using analytical equations or computer simulations. Analytical equations work well for isotropic materials like titanium, but are not as reliable for thick composite structures like the CFRP cylinder. Computer simulations can be categorized according to their order of fidelity, like low, mid, and high fidelity. The analytical equation shown here is only valid for isotropic material and is not compatible with the CFRP material description, which requires multiple material parameters. But using the well-known ABD stiffness composite matrix, we can treat CFRP as an isotropic material, as we assume the individual laminate layers can be smeared to a quasi-isotropic material. The analytical buckling pressure is estimated to be 84 megapascals using the methodology. In the simulations, three main aspects are considered. The first aspect is buckling. The linear buckling analysis results in a design pressure of about 70 megapascals, depending on the order of fidelity. The design of the CFRP pressure vessel is usually divided into three regions: the limit load, the ultimate load, and a safety reserve. The limit load is the operation load of the Titan, which is assumed to be 40 megapascals, which corresponds to the pressure that we would expect at the depth of the Titanic. The ultimate load is the product of limit load times a safety factor, which was 2.25, according to an article in Composite Worlds. The Composite Worlds article stated that a safety factor of 2.25 for a thickness of 114 millimeters was established for the CFRP cylinder, but the thickness of the CFRP cylinder was increased to 127 millimeters for additional safety. However, the results of analytical equation and simulation show much lower loads than we would expect. If we have 90 megapascals for a thickness of 114 millimeters, the maximum pressure in the safety region would be 112 megapascals for a thickness of 127 millimeters. Instead of 90 megapascals, our simulation shows 74 megapascals, and even if we increase the thickness to 127 millimeters, we barely get about 90 MPa as a design load. The second part of the simulation involves material strength. In the case of CFRP, we consider fiber as well as matrix fracture in tension and compression. Using this methodology, we get a design load of about 74 megapascals. If we consider imperfections as a third aspect, the design load is reduced even further. The well-known energy barrier criterion, EBC, delivers a design load of 56 megapascals. There are still some open aspects like 1. Variation of material data, 2. variation of wall thickness, 3, effective temperature, 4, effective dry-wet cycle, 5, adjacent structure influence which is not considered and the design factor is already lower than 1.5. What has the CEO of OceanGate to say about this rather low margin of safety? Because of this statement, I wanted to interview Stockton Rush, the CEO of OceanGate, and flew all the way to Borneo to meet him. You might think that this Stockton Rush is washing socks as some kind of circus trick, but not so. He is preparing the manufacturing process for his submersible Titan. Mr. Rush, how would you connect the CFRP cylinder to the titanium domes? Can you show me? Well, that went differently than expected. Let's show Stockton Rush how to learn proper engineering with today's sponsor, Brilliant. Your ultimate online resource for all things STEM, science, technology, engineering, and mathematics. Whether you're passionate about mathematics, science, computer science, or data analysis, Brilliant has you covered with over 100 different courses tailored to your needs. Dive into the world of math, where complex concepts become clear and intuitive through interactive puzzles and challenges. Master computer science and programming languages with hands-on exercises and real-world applications, turning coding novices into programming pros. Unravel the secrets hidden within data with our comprehensive data analysis courses, equipping you with the skills to interpret and manipulate data like a seasoned analyst. And for educators, Brilliant offers resources to enhance your teaching, including tools to help your students understand graphs with clarity and precision. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org.ronaldwagner or click on the link in the description. You'll also get 20% off an annual premium subscription. You might think, okay, the safety factor is about 1.4. What is the problem when I never dive deeper than the 4,000 meters anyway? The problem lies in the assumption that you know and understand everything. The Titan dived multiple times to the Titanic and was tested in the Deep Ocean Test Facility, but this is not a proper test program according to engineering standards. Here is what a proper engineering test program for a manned submersible looks like.
Doing one dive to 4,000 meters is not a test program. A proper test program on any pressure vessel that is new, that we don't know how it behaves, is you've got to do 3 tests. The first one is you've got to blow up 5 units. You've got to crush them. And you've got to find out that the crush pressure actually matches your calculation. If it's all over the place, it means your calculations are no good. The second one is you've got to put it under constant pressure for 3 months at 6 times the pressure, because plastic, you've seen it, it creeps. It just keeps moving. So it's like, well, it might be good for the first hour, but after 4 hours, all of a sudden it deforms and it collapses. So you've got to put it for 3 months under on 6 times the design pressure. And after that, you got to cycle it at full pressure for 1,000 times. Well, that takes better part of 2 years to do that.
As we have heard, the ASME design codes require a safety factor of 6, which would lead to a much thicker CFRP cylinder than the one the Titan had. The most likely cause for the implosion of the Titan was cycle fatigue damage. That means that over time, damage accumulated in the CFRP cylinder from each dive, which led to the final failure of the submersible. The debris of the Titan consists of the front hemisphere, without the acrylic viewport, the tail section, panel parts, the support legs, and the interface rings. Neither the CFRP cylinder nor human remains were found. The implosion leads to a sudden change in pressure, which is, even for small pressure differences, devastating on the human body. This diagram shows that a pressure difference within 1 meter from the origin of about 1 megapascal is already deadly. At the depth of the Titanic, the pressure difference is nearly 40 times higher. Even a pressure difference of about 200 kilopascal within a short distance of the pressure difference would lead to the collapse of the lungs. This table here lists different TNT charge weights and distances from the pressure difference. According to this table, the Titan implosion at the depth of the Titanic is about as bad as standing near a 1-ton TNT charge. This implosion simulation shows first the collapse of the CFRP cylinder, and afterwards both hemispherical caps move in together, the panels are mostly destroyed, and the support legs are ripped off the pressure vessel. The whole process from CFRP cylinder fracture to complete implosion takes only 6 milliseconds. The human brain needs about 30 milliseconds to process images and about 100 milliseconds to process pain, so the crew of the Titan neither saw what was coming, nor did they feel anything.